Okay, let me welcome all of you back from back to the organic chemistry session after the snowstorm of Tuesday. Okay, today we are going to finish up on chapter 14. And then after chapter 14, we shall go to chapter 15. Start with chapter 15 today. Okay, I do also have a couple of announcements. The homework assignment, the chapter 14 homework assignment, the due date for that has been rescheduled for Sunday, January 26th at 11 p.m. Okay. So what that means is we are not going to have our assignment for chapter 15. The next our assignment will be on chapter 16, 1-6. Okay? Because we are one lecture behind already. Okay, you have a question? I can hear you. Well, why don't you come and see me in the office? Okay, so let us get this session started. When we left on Thursday, we were discussing a Diels-Alder reaction. So what we want to do today, we are going to finish up on Diels-Alder reaction and then discuss a few other topics in chapter 14 before we go to chapter 15. To do that, what I want to do, I want us to go over a problem set that is in the back of your book. Okay, to get the session started. Specifically, I really do want to see whether you guys have forgotten everything we discussed on the Diels-Alder reaction. So we are going to start with this problem here, and this problem has a specific question on Diels-Alder reaction, that is this one here. Okay, Mashake, can you go ahead and read this first? Okay, thank you. So what this question is asking you, see what products would you expect to obtain from reaction of 1,3 cyclohexadiene with each of the following reagents right here. Okay, so the first thing we need to do here, we need to know the structure of 1,3 cyclohexadiene, right? Okay, and that will be this here. It's a 6-member ring molecule, the cyclohexadiene 1,3. So we have a double bond here, another double bond here. So this will be a conjugated system. If we number the carbons, you say this is carbon 1, carbon 2, 3, 4. Okay, we call this carbon 5. This is carbon 5 and carbon 6. And then let us take a look at question 21E, this one here. 3-butene 2-on, which is this molecule here. So what they want us to do here is to perform a Diels-Alder reaction between this 1,3 cyclohexadiene and the 3-butene 2-on, which is this here. Okay. Of course, we have CH2 here. Okay. So what do you think the product will be? Let me go ahead and number the carbons of the dienophile. Of course, this is your diene, and this is your dienophile. Okay. Let me go ahead and number this carbon here. Let us say this is carbon number 7, and this is carbon number 8. Okay? Okay, according to the Diels-Alder reaction, we are going to form a 6-member ring. Okay, can anybody tell me which carbons of the diene will be attached to which carbon of the dienophile? 1 and 8? Very good, very good. So you say we are going to have this. One and 8, and which one? 4 and 7. Excellent, excellent. So we are going to have an attachment between 1 and 8 and 4 and 7, and then the new carbon-carbon double bond that will be formed, where would that be? Between 2 and 3. Very good. So right here. Okay, excellent. So let us see the product. So we have this. Okay, we have, let's number the carbons. This would be carbon 1, carbon 2, carbon 3, carbon 4. So I am going to call this carbon 7, belonging to the dienophile, and then this is carbon 8, right? And you told us that the double bond, the new carbon-carbon double bond, will be between 2 and 3, right? Okay. So let us place that in there. Between 2 and 3. Okay. Now we now have this group here. This group here will now be here. Of course, we know on carbon 7, all we have is 2 hydrogen atoms, right? Okay. So what is missing here? What is missing here? Carbons 5 and 6, which will make up the bridge, right? So therefore, let us place the carbon 5 and 6. So we say we have this here. Okay. So now this is 5 and this is 6. Okay, is that correct? Okay, supposing I want you to draw the 3-dimensional structure for this product. Okay, what will it look like? In other words, you want to look at the product from the side rather than looking from the top. Okay? Okay, what would that look like? So it looks like this. Okay. Let us number the carbons. This is 1, 2, 3. This is 4. Now, what carbon is this? What carbon is this? What is it? Carbon, this one here. 7, exactly. So this is 7. About this? 8. Okay, good. And about this carbon here? 5. And this is 6. So 5 and 6 will be the bridge carbons, right? Now, what kind of product are you going to form? This group here, will it be in the endo position or the exo position? Endo or exo? What position will it be? Endo, okay, away from the bridge, right? Okay, so therefore we expect that to be here. Of course, the hydrogen will be in the hydrogen here will be in the exo position. Okay, so this is the endo position right here. Okay, everybody agree? So you could see here, we could also give you this structure here and ask you to give the starting material. In other words, we could give you the product of a Diels-Alder reaction and ask you to give the starting material that was used to make the Diels-Alder product. Okay, now, if you look at this question here, you have a lot of reagents here that most of you will say, well, we did not do this semester. But all of these reagents we used last semester. The reason I want to bring up this problem here is to let you know that everything we did last semester, you need to know that. Keep in mind, the final examination will be based on a comprehensive content, including everything we did in Organic 1 and Organic 2. So all of these reagents, you need to know them. So let us take a look at this reagent, just as a form of review. Everybody got this? Okay. Let me see this here. Oh, by the way, did I put a double bond? Okay, let me go back to that. You guys will remind me if I do make that kind of mistake. Okay, let me... Okay, let me redraw that molecule again. It should be this here. The double bond will be here, and of course you have the endo product. The hydrogen is here, okay? And we said this was carbon 1, 2, 3, 4, 5, 6, and then we said this was, I believe we said this was 7, was it? Did you say 7? Okay. And this was 8. Okay, so make that correction. I was missing, in the last structure I gave you, this double bond was missing. Okay. Now let us do this one here, F. Hopefully this will be a review to all of you. Okay, we have step 1, osmium tetroxide, followed by sodium hydrogen sulfide. Okay, the question I have for you is this: what does this reagent do? Osmium tetroxide. You need to know what those reagents do. What does it do? What does it do? It adds 2 hydroxy group across the carbon-carbon. Very good, excellent. How does it do it? I mean, in what way does it do it? The syn addition. Okay, very good. In other words, those 2 hydroxy will be on the same side of the molecule. Okay, very good. Once you know that, then this problem is easy. So in this particular instance here, you have to know what this reagent does. Okay, so what it does, it adds two hydroxy group across a carbon-carbon double bond in what we call a syn addition fashion. Syn addition of two hydroxy groups across a carbon-carbon double bond. Okay? You need to know that. So that also tells us that on this carbon here, since we have a double bond here, we are also going to have this. Is that clear? Okay. Now let us do A. Let us do A. No, I'm sorry. Let us do B. Let's do B first. Yes.
Do you have to show like this?
No, in this particular instance, no. No. Unless I ask you to do that.
Okay.
Okay. Take this out. Okay, so let us do B. Step 1, ozone. And step 2, we have zinc. Generally, you use this in the presence of some kind of dilute acid. Okay, so what does this reagent do? What does it do? Cleave a carbon-carbon double. Excellent. This reagent, what it does is to cleave a carbon-carbon double bond, okay, such that the carbon that has a hydrogen atom attached to it, that carbon becomes the carbonyl of an aldehyde, okay? And the carbon that does not have hydrogen attached to it becomes the carbonyl of a ketone. Okay, so keep that in mind. So that is what this reagent will do. It will also cleave this right here. So there, what do we have? We have this. Okay, from this part of the molecule, right here. And then from this other part of the molecule, we have this. Okay, so if we number this, this will become, if we say this was carbon number 1, 2, 3, 4, 5, 6. So here, what carbon is this? What carbon would it be? 2. Carbon 2, very good. So this carbon 2, and therefore this carbon 3. And what carbon is this? 1, very good. This is carbon 1, and therefore this is 6. This is 5, and this will be 4. Okay, so you can follow that. Okay, so what this reagent does is to simply cleave a carbon-carbon double bond. So keep that in mind. You need to know your reagents. Okay. Okay. Now let us do one more of this problem here before we go to something else. How about D? This here. D. Okay, for D we have deuterium chloride, D chloride. Don't forget deuterium This is the isotope of hydrogen. Okay, or the proton. Okay, so you simply have to treat this here just as you would treat the hydrogen chloride. Okay. Okay, so what kind of reaction do you expect to get here? I'll give you a clue. You get a 1,2 addition and a 1,4 addition. Let us number this here. Carbon 1, 2, 3, 4, 5, and 6. Where would the deuterium go? Carbon 1. Why? That is correct. Why carbon 1? Because we form a more stable carbocation. Okay, right? Because here, when deuterium goes to this carbon here, carbon 1, the positive charge will be on this carbon here, and that is allylic. But if you went to carbon 2, it will be going here, and that is not allylic. So keep in mind, anytime you perform a reaction in which you are going to form a carbocation, the more stable carbocation will be formed initially. Okay? Okay, so therefore, we expect here, if deuterium goes to carbon 1, for the 1,2 addition, the chlorine will go to which carbon? Carbon 2, right? Okay, so we do expect to get this. So deuterium goes here, and the chlorine goes here, and then the double bond is still here. That is a 1,2 addition product. Okay. How about the 1,4 addition product? If the deuterium goes here, right, we form a carbocation here, and as a result of resonance, this pi electron moves to here, to between 2 and 3. Therefore, you are going to generate a carbocation on carbon number 4. And then the nucleophile, which is the chloride anion, will attack carbon number 4. So therefore, so we expect to get deuterium is here. And the double bond will be here, and therefore the chlorine will be here. So this is the 1,4 addition product. Okay? Okay. Now before we leave this, there is a couple other features of the Diels-Alder reaction I want to introduce to you. Okay, this is the more, let's say more on Diels-Alder reaction. If you have this, notice that most of the reactions that we have been giving you, we have the carbon-carbon double bond on the same side of the single bond. Okay? This here we call a cis, in this case we say this is a cis conformation. As opposed to if you have a single bond and then double bond is here and double bond is here, in this case, think of those two double bonds on opposite sides of the single bond, right? And therefore we call this the trans conformation. It also happens that Diels-Alder reaction will only take place whenever the molecule is capable of assuming a cis transformation. In other words, this molecule here is in equilibrium with the cis conformation, will be in equilibrium with the trans conformation under normal room conditions. Okay, it goes back and forth, and this is the conformation that will undergo the Diels-Alder reaction. So essentially, what you have here, we are simply rotating this single bond, rotate the single bond so that it goes from the molecule goes from the trans conformation to the cis conformation. Now, on the other hand, supposing we have this, let us call this molecule A. Okay, will molecule A undergo Diels-Alder reaction? Is it capable of undergoing Diels-Alder reaction? Yes or no? We told you Diels-Alder reaction only takes place when the molecule can assume the cis conformation. The answer is no, right? No. Because this molecule, the configuration is fixed. Okay, you cannot rotate this bond because it's part of a ring system. You cannot rotate that bond. So this molecule here cannot undergo Diels-Alder reaction. So I'll say will not. Undergo Diels-Alder. Okay? Will not undergo Diels-Alder. Keep that in mind. The only time a molecule will undergo Diels-Alder if it is possible for that molecule to assume a cis conformation. Okay? This here, this molecule here, even if I gave you this molecule in this form, this molecule is capable of rotating this single bond to give this here. Therefore, it will undergo Diels-Alder reaction. Okay. About this molecule here, supposing I give you this. Okay. This type of molecule also will not undergo Diels-Alder reaction because if we rotate this molecule will be in equilibrium with the trans conformation, which will be this here. See the trans conformation, and this is the cis conformation. It also happens because of what we call steric hindrance. Let us call this molecule A, and let us call this molecule B. Yes. Molecule A, yes. With this, the thing. Yeah, it goes. Yeah, it goes back and forth. Which arrow? This here? Well, you know, this you are simply just saying that you are rotating this. You don't need to do this. Okay. All you're doing here is that, you know, when you do this here, it's in equilibrium. And the only way it goes from here to here is because you are rotating, or the molecule is rotating by itself. It is rotating the single bond. Okay. See that? Oh. Thank you. I didn't mean to do that here. Thank you. Okay, this is supposed to be this here. Okay, this is supposed to be this right here. Okay, we have a double bond here. We have another double bond right here. And this is coming here. And this is going here. Okay? So this is the trans conformation, right? Now what you have here, because of what we call steric hindrance, this is A and B. This molecule prefers to be in the trans conformation. Okay? This molecule here is going back and forth. It prefers to be in the trans conformation because when it is in the trans conformation, these two methyl groups do not bump into each other. Okay? And that is what we mean by steric hindrance. Okay? So this molecule prefers to be in the trans conformation. Okay? And because it prefers to be in the trans conformation, it will not undergo Diels-Alder reaction. Okay. Okay. Is that clear? Okay, now there is another problem I want us to solve, also from the back of your book. Everybody clear on this? You still writing? Let's go to this one here. Okay, Hangings, can you go ahead and read this for us? Oh, can you read it? Oh, you can? Okay, let me get somebody closer. Shante, can you read this for us? You can read it. Okay, proposed structure for limonene, right? Okay, very good. Now, what they've told us here, they've given us this molecule here they call limonene. It has a molecular formula of C10 and 16 hydrogen. Okay, now they say this molecule, limonene, when they do hydrogenation, it gives another molecule with a formula C10 H20. Okay. Okay, but before we get to this reaction, before we get to what this actually means at this point, let us take a look at this information they've given us. It said limonene has no ultraviolet absorption maxima above 200. Okay, so let me take a few minutes to give you a background information on this. So I'll call this conjugated system. Conjugated system and ultraviolet spectroscopy. Okay? You know, we told you, remember we told you, let us use this schematic here. Energy here. We told you, in order for you to have a conjugated system, you must have at least 2 carbon-carbon double bonds that are separated by a single bond, right? And each one of those carbon-carbon double bonds, you have a p orbital on each one of them. Okay, so let us say here, we have p orbital here. And each one of those p orbitals, we told you that we have an electron. We also told you, in order for you to have a p orbital, there is a side-to-side overlap of those p orbitals, in which 2 electrons are being shared within the overlap orbitals. Okay? So now let us think of it this way. Give you another schematic here. Think of this as your overlap orbital. And now you have 2 p orbitals. Just let me now. Right here. Okay, this is your overlap orbital. Overlap p orbital, in which you have 2 electrons. Supposing you now expose this molecule to ultraviolet light, it's called UV light. What is going to happen? These pi electrons here, keep in mind, since we are now forming an overlap, we don't have pi electrons. One of these pi electrons here could be promoted to what we call an excited state. Okay, so we see one here, the other one will be here. Now this is your pi electron, and this is what we call your pi star electron, which is an excited state. And that transition from pi to pi star electronic energy level, you could get all of that energy from the UV absorption. Now, the point we made here is this. If you take a look at your UV spectrum, it goes from 200 nanometer to 400 nanometer. So you have a sample inside the spectrometer, right? You're scanning through with the light having energy between 200 nanometer to 400 nanometer. So the moment you get to a point when that molecule is absorbing UV light, you get something like this. Okay, so now you refer to this as your absorption maximum. So in this particular instance, we will say, okay, this molecule here is absorbing probably at about 250 nanometers. And this is here what we call the absorption maximum. Now the point here is, only conjugated systems will absorb UV light. Okay? Anytime you are told that this molecule is absorbing UV light, what does that tell you? It is simply telling you that molecule is conjugated. Okay? Okay, now let us go back to the problem. Okay, well, before we do that, supposing I give you this. Do you expect this molecule to absorb UV light? Yes or no? No. Okay? About this one here. Do we expect that molecule to absorb UV light? Yes. Okay, this will absorb, and this will not, because this is not conjugated. Okay, so let us go back to that problem. Okay, so now they told us limonene has no ultraviolet absorption maximum above 200, because the ultraviolet absorption is between 200 and 400. What they've told us here is that limonene is not a conjugated molecule. Okay, very good. Now, they also told us that limonene, when undergoes hydrogenation, gives to this molecule here, let us call limonene molecule A, and the product of hydrogenation, let us call the molecule B. Okay? I have a question for you. What is the index of hydrogen deficiency of limonene? Index of hydrogen which we call IHD. What is the index of hydrogen deficiency of limonene? What is it? 3? Okay, for those of you who are not in my class last semester, this is the formula for that. Index of hydrogen deficiency, IHD, also number of carbon atoms in the molecule, minus number of hydrogen atoms in the molecule, minus number of hydrogen atoms in the molecule divided by 2, minus number of halogen in the molecule divided by 2, plus number of nitrogen divided by 2 plus 1. Okay, if you use this formula here, you will find out the index of hydrogen deficiency of limonene is 3, just like you guys have already told us. Okay, now, they told us that limonene reacted with hydrogen to give compound B. What is the index of hydrogen deficiency of compound B? What is it? 1, exactly. IHD, if you work that out, equals to 1. So what is this telling you about limonene? Limonene must have a ring. That's what it's saying. And of course, either 2 double bonds or a triple bond, right? But the most important information here, limonene has a ring. Okay, so let us put that down. Okay, so keep that in your mind right here. Then how do we solve this problem? Now they told us that limonene, we now have limonene again reacted with ozone, right? Step 1, ozone. Step 2, zinc. To give this here, let us call this compound A. Let us call it West. Let's call it C. To give formaldehyde C and this diketoaldehyde, what they call diketoaldehyde, this here. Let us call it D. Okay? So it gives C plus D. Now they say, give the structure of limonene. Okay? So let us see, how do we approach this? The first question you ask yourself is, this here. What does this reagent do? Give carbon-carbon double bond, right? That's all it does. Okay? Limonene did not have carbon-oxygen double bond to start with. there was no oxygen in limonene. So if one of these carbon-oxygen double bond, therefore, must be a result of this cleavage, right? You follow that so far. If you do that, let us see now. If you follow that, then I will say, okay, if that is the case, let us start with some assumption. I will say, supposing this carbon-oxygen double bond and this carbon-oxygen double bond, they came from one carbon-carbon double bond. So let me go ahead to make this easy for you. Let me go ahead and number this carbon here. Okay, we say this is carbon 1, 2, 3, 4, 5, 6, and 7. Okay? Well, I tell you what, let me do this better than that. I don't want to confuse you. Let us start with this carbon here. Let's start with the carbonyl carbon. Okay? Let us say this is carbon 1, carbon 1, carbon 2, carbon 3, 4, 5, and 6. Okay? So at this point, I want to make an assumption that we are going to form a carbon-carbon double bond right here between these two carbonyl. Let us start with that assumption. So if we do that, what is the size of the ring system we need to form here? How many atoms in the ring system? 6. Oh, very good. So let us go ahead and draw a 6-member ring. Okay, we draw a 6-member ring, and the double bond is between what carbon? Between what carbon? 1 and 6. Okay, so we place a double bond here. Okay, so right away, let us say this is carbon 1, right? And carbon 6. Is that right so far? Now, if that is the case, this methyl group is attached to what carbon? Carbon 1. Okay, so let us place the methyl group here. Okay. So on this carbon here, all we have is hydrogen. Okay. Now, so if that is the case, then let us now number the rest of the carbon in this molecule. This is carbon 1, therefore this is carbon 2, this is carbon 3, this is carbon 4, right? This is carbon 5. So far so good. Okay, now, this group here, what carbon is this group attached to? What carbon? Carbon 4, okay? So let us place that here. So far so good, right? Okay? So now we've explained this part of the molecule, right? Now, they also said that this reaction formed formaldehyde, right? So what we need to do now, we have this carbonyl and this carbonyl, we join them together, right? Because they must come from the cleavage. Okay? So if that is the case, follow me now, right? I will take off this here, right? And I join this carbon. Okay? So now we see, let me declutter this place so it doesn't look so cluttered right here. Take all of this out. Okay. Now we see. if everything we are saying is correct, this is limonene, right? Right? Now, let us see whether this is correct. Now they say, this compound forms an acara. Acara product when you treat it with hydrogen and catalyst, right? Okay, so what does that mean? That means that they did this right here, perform hydrogenation. Okay, when hydrogenation was performed, what happened? What's going to happen? The double bond will be gone, right? Right, okay. So now we have this. Now, if you follow what we have been doing, keep in mind we said limonene is compound A. That's what we said here. So this is compound A. And we said the product of hydrogenation is compound B. Sorry, this is gone. Okay? Because what did we do with hydrogenation? This double bond is gone. This becomes a CH3. That's what we have there. And this double bond is gone. And they say this compound here is an acara molecule. If you recall what we did, once again I want to let you know that you not forget everything we did in organic 1. Acara. What does acara mean? It will superimpose on its mirror image, right? The chances are it does not have a chirality center. Okay, so it does not have a chirality center. Okay? Look at the product that we have here. Does it have a chirality center? Does anybody say chirality? A chirality center, by the way, is that carbon atom or that atom that is attached to 4 different groups or 4 different atoms. Okay? If you look at this carbon here, this is not a chirality center, because if you look at this part of the molecule, this is a symmetrical molecule. Okay? If you look at this carbon here, that is not a chirality center, because this molecule is symmetrical. This part is the same as this part. So far, this is consistent with the information they have given us. So therefore, we are right by saying molecule limonene is molecule A, right? And some of you will say, okay, why don't we join this carbonyl and this carbonyl and see what we get? Okay, so I will give that to you as an assignment. When you go home, try to see whether that will be right. Okay, try to join this carbonyl here and this carbonyl and see what you get. I guarantee you, yes, whatever you get after you do hydrogenation, you are going to have chirality center. Yes. Where's the oxygen? In which molecule? You say, where is the oxygen, right? Which molecule are you referring to? Is it this molecule A, right? Or molecule B? You say, where is the oxygen? Which oxygen are you referring to? No, okay. The oxygen are the only way you have oxygen, these are in the product of ozonolysis, right? You have oxygen here, oxygen here, oxygen here, and oxygen here. Those are results of cleavage of carbon-carbon double bond. And what I've done here is to simply tell you, supposing we have a carbon-carbon double bond here, And that's what we have here, right? And then we say that this here and this here form a carbon-carbon double bond, and that's what we have here. So you cannot have oxygen here. I tell you, why don't you come and see me in the office? Okay, anyway, so you follow this. So these are the kind of things that you need to think of. This is the kind of problem we refer to as a roadmap problem. You will be getting this kind of problem in your exam. Okay, and for you to be able to do this, you need to know those reagents, what they do. Of course, then you have to bring in some critical thinking in this kind of problem also. What time do we have? Oh, we've got plenty of time. Okay. Okay, before we leave chapter 14, I do have a couple other concepts I want to share with you. Actually, it's one, just one. Okay, this is a polymer. Formation. Polymer formation. Remember, so far we have given you a conjugated system in which electrophilic addition reaction we have 1,4 addition or 1,2 addition. We could actually use this reaction here to form some very important commercial products. Say, for example, you have this. This molecule is called isoprene. Supposing I have a proton, say from hydrogen chloride, right? Keeping my hydrogen chloride is proton plus chloride. What do you think is going to happen? Hydrogen chloride here. What happens? The carbonyl will attack the proton, right? Okay? Carbonyl attack this here to form a carbocation on this carbon. Okay? But once it does that, because you have conjugation with this carbon-carbon double bond, this here, this bond will move to here. And what do we get? Now get this. From that. Now what happens if another molecule, let me number this to make it easy for you. Let us call this carbon 1 right here. Okay? Carbon 2, carbon 3, and carbon 4. Okay? Supposing another molecule of isoprene comes in, okay, this carbon double bond will now act as a nucleophile, right? Just as it did here, attacking the proton, it could also attack the carbocation. So what do you get? You get this. another carbocation. Let us number the carbons. This is our carbon 1, right? Carbon 2, carbon 3, carbon 4. Okay? And let me also number number this one here. This is also 1, 2, 3, and 4. Okay, so now we also now have this, another 1, 2, 3, and 4. So what do we have here? We have a 1,4 addition reaction taking place. Supposing we now have another molecule of isoprene. Another molecule of isoprene. What do you think will happen? What do you think will happen? Let me number this again. 1, 2, 3, and 4. What will happen here? Okay, another nucleophilic attack on the carbocation. Very good. Now this process that I'm showing you here, this is the process of polymerization. In other words, you are starting with a small molecule and then we're building a bigger molecule. And so what we have here, okay, at the end, let us imagine that at the end, this chloride here simply comes in to attach itself to here to stop the process. Now, each one of these units here, okay, let us say this 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, and 4. Each one of these here is what we call a repeat unit. To simply just do this right here. This is what we call a repeat unit, or referred to as a monomeric unit. In other words, the isoprene is what we call a monomer. And guess what? Look at this molecule that we formed here. This is your rubber. You know the rubber that you use for your tires? That's how they are made, right here. Okay, you didn't know that isoprene. When you ride those cars, this is what you are riding, right? This is how we made them. And it is made using the 1,4 addition reaction involving a series of isoprene units. And when you see a crack on your tire, right, on the side tire, if you have been using that tire for a long time, guess what is happening? And you have a lot of pollution in the atmosphere. All those ozone that you see in the atmosphere, what is happening? They are reacting with those double bonds in your tire and splitting them into carbonyl, and that's why you begin to get cracks. Okay? So this organic chemistry does have some important utility, both commercially and also in industrially making all those pharmaceutical drugs or commercial products, just as in the case of rubber. So anyway, you see here, very simple reaction, 1,4 addition reaction, giving you a very, very important commercial product, just like rubber. And when your tire is cracking, you then say, okay, there's ozonolysis taking place here. The ozone in the atmosphere is reacting with the carbon-carbon double bond on my tire and splitting those tires into cracks. Okay? So anyway, so this is the process of polymer formation or polymerization. sometimes we refer to this as polymerization. And this particular reaction could also be initiated with a free radical. Instead of using a proton here, you could start with using a free radical. You could have free radical polymerization. Is also possible. Okay? Okay, at this point we have finished chapter 14. So now we have plenty of time to start chapter 15. I think we have about, at least I get a chance to introduce chapter 15 to you. And the chanter is laughing. Oh, plenty of time. I go there 15 minutes, yes. Yeah, go ahead. You got to talk loud because this year I can't. Oh, okay. Very good question. So the question that you have been asked here is it because isoprene is so reactive, much more reactive than chlorine, right? What happens when you do this reaction? You want the hydrogen chloride, or if it is your initiator, right? Very small amount. There's so much isoprene in there because all you need is just to start the process. Once the protonation takes place, you form the carbocation, the isoprene will take over. Just as long as you have isoprene in there. So depending on the type of rubber you want to make, it depends, you could have the ratio of whatever isoprene you have in there. And the same thing applies to all types of polymerization. So you could actually engineer it to give you the particular product you want, depending on the starting material ratio. When when all the isoprene is gone, then the chlorine comes and attack itself to the end. That's the end of the process. Okay. So now let us. I will take just a few minutes to introduce you to chapter 15, and then I will stop to give you back your quizzes. Okay, I do want to call your names so I get a chance to know you guys. Oh, by the way, there should be, when you do this, there should be some kind of N here. N meaning that N could be more than 1,000 units, Let's say N equals to 100 or greater. Okay? Okay. Chapter 15. So at this point, you guys should be able to do all of those problems set in R, and that is why I extended the assignment till Sunday. Okay, so with chapter 15, what we want to do here is begin a discussion of what we call aromatic compounds. For the most part, our focus will be on benzene and benzene type molecules. The benzene and derivatives. Of course, like every class of compound that we deal with, we will discuss the nomenclature. And then, of course, we will discuss very briefly what makes a molecule aromatic, which we call aromaticity. And then finally, for this chapter and also chapter 16, we will be discussing the reactions of aromatic compounds. Okay, you know what this list is? This is a list of learning outcome objectives. For example, at the end of this chapter, you should be able to identify the conditions that make molecules aromatic. When I say a molecule is aromatic, exactly what do we mean? Okay? So take some time to take a look at this list and then use this as a study guide. Okay. The question is, we want to start studying aromatic compounds. What do we mean by aromatic compounds? What do we mean by when we say molecule is aromatic? Okay, what I want to do now, even though I've sort of given you a definition here, I'm going to give you a few requirements that make a molecule aromatic. First, the molecule will be unusually stable. When we say unusually stable, that is compared to similar molecules. I will tell you what we mean by that shortly. 2. The molecule must be contain a cyclic, let me take that, contain a planar cyclic ring system. What do I mean by planar? Look at this ring system here. This is flat. That's what we mean by planar. Okay? All of the atoms involved in this particular molecule here, they are on the same plane. So this is flat. For those on that side. Okay? So the molecule must contain a planar or planar cyclic ring system. 3. All atoms in the ring system or in the cyclic system, since I want to use cyclic, in the cyclic system must be sp2 hybridized. Must be sp2 hybridized. 4. The pi electrons or the non-bonding electrons in the cyclic system, must be capable of delocalization. Must be capable of delocalization. Delocalization. In other words, if you have this pi electron here, they should be able to move all the way around this ring system. Okay? Finally, the cyclic system must have cyclic system must have 4n plus 2 pi electrons. Okay? If I number this, let me go ahead and number this. So 1, condition 1, 2, 3, 4, and 5. This condition 5 is what we refer to as Occult's rule. In other words, we say that the molecule must obey Occult's rule. Now, what do we mean by 4n plus 2 pi electrons? 4n plus 2 pi electrons where n equals to 0, 1, 2, 3, in other words, any integer or any integer is a whole number. Okay? Now, let's just look at all of this. Have you written all this down? Okay. Let's look at the first one. Unusually stable. Let us take, for example, if you have this, just for reference, take this carbon-carbon double bond, right? Hydrogen with platinum. What do I get? What happens? I reduce that molecule. The double bond is gone, right? We add hydrogen across the carbon-carbon double bond. If I add this molecule, the conjugated system, by the way, I do the same thing, hydrogen, platinum, I'm able to do this. At ordinary conditions, generally, we could do this at almost room temperature, very low pressure. On the other hand, if you take this molecule that we call benzene, and you do the same thing, no reaction. At ordinary conditions. In order for you to get benzene to react under degeneration conditions, you have to use very high temperature and very high pressure. Okay? In other words, benzene is so aromatic, it will resist any attempt to reduce its what we call aromaticity. And I just introduce another terminology to you. I say aromaticity. All of these conditions here that make a molecule aromatic, we refer to this as aromaticity. In other words, when we say a molecule shows aromaticity, it shows that all of these conditions must be met. Not just one of them. All of these must be met. If I say this molecule shows aromaticity, in other words, it means that it is visually stable, contains a planar cyclic ring system. All the atoms in the ring system must be sp2 hybridized. The pi electrons are capable of delocalization, and importantly, it must have 4n plus 2 pi electrons. Let us take a look at this last one here, number 5. Using benzene. If you take a look at benzene, the molecule that we refer to as benzene, how many pi electrons does it have? Keep in mind, each one of these is 2, right? How many? 6, okay? So according to Occult's rule, it has 4n plus 2 pi electron equals to 6. Okay, let us solve for n. If you solve for n, n equals to 1. So that means this molecule obeys Hawkins rule. As long as n equals to 0, 1, 2, 3, whatever, then you say it obeys Hawkins rule. So benzene obeys Hawkins rule. And also, if you take a look at benzene, keep in mind that each one of these benzene molecules here, right here, we have this p orbital here, p orbital here, p orbital here. But what happens? All of this contains electron, right? Okay? You guys are moving, must be. Okay, let me just finish this point and then we'll. Okay. The point I want to make here is that all of the pi electrons in benzene are capable of electron delocalization. Keep in mind that if you have this will overlap with this will overlap with this will overlap with this. If it does that, then we have this molecule here. On the other hand, this overlap will also be here. Okay, we have electron here, 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 and here. So this overlap will also be here. This here, and this here, and then you have this. These two structures here, let us call this A and B. These are resonance structures for benzene. In other words, what we are saying here, because of resonance, benzene is unusually stable. Okay? And that is why it does not undergo the regular reactions of the carbon-carbon double bond. So when we come back on Tuesday, we are going to continue on chapter 15, and there will be a short quiz on Tuesday based on what we discussed today. Do not forget, I need to give you back your quizzes.